So hello everyone, my name is Pierre Guilmin. I'm a PhD student with Pierre, whom you met for the first lectures on stochastic master equation. And I'm also working with Antoine Sillois, who will be joining us next week. I'm doing my PhD in Paris with Min Paris Institute, INRIA and ENS. And I'm also working with a startup called Alice and Bob. So I'll tell you a little bit more about what we do there. So this talk, for the end of the afternoon, is about how to estimate parameters of a continuously measured quantum system by fitting the correlation functions of the continuous measurement data. So I've planned a fairly long introduction to superconducting circuits, how complex they can be and why we want to build them. Because I think it's important to have the context of why we think this new method is interesting. So I'll first start with experimental quantum error correction with superconducting circuits. So today, I think most people building superconducting circuits have the aim to build a fault-tolerant quantum computer. And so, as you all know, qubits suffer from two kinds of errors, bit flips and phase flips. But there is a solution, which is to use quantum error correction. And a global way, a general way to phrase what quantum error correction does is that you are going to encode your information in a very large Hilbert space in which you have local errors and uncorrelated errors. And so by delocalizing your information, you're going to be able to protect from it. So maybe the basic example is to say you have a qubit, it's interacting with its environment, and so it has this bit flips and phase flips error on the block sphere. But now if you put many qubits together, so this is C2, you put many of them together. If you suppose the errors of this qubit are local and uncorrelated, by building this very large Hilbert space, so here the quantum error correction Hilbert space will be C to the power 2n and the number of qubits, you'll be able to delocalize the information and protect from these errors. So this will be my first example of superconducting circuits, how we can use transmon qubits and basically the surface code, which is one kind of error correction protocol. But I will also give another example, a bit more exotic and a bit more recent, based on bosonic codes. So you heard about bosonic codes during the talk of Barbara Terral about GKP qubits. And here the general idea is to say, well, I want to protect from local errors. What if my qubit was encoded in a larger Hilbert space? So for example, the Hilbert space of a harmonic oscillator. So here your Hilbert space is spanned by the Fock state. And if the error processes in this Hilbert space are local, so you can think of the A dissipation operator, maybe I can find a good encoding of my information. So non-local encoding of my information in this space that will protect from this local error. Okay. And so, okay, maybe to give another intuition about local and non-local errors, if you draw the phase space of this oscillator, say you have some quantum state somewhere. A local error is something that is going to locally shift or move your state. This is what I call a local error. And then a non-local error is something that will make you state move, like teleport to another place in phase space. This is unlocal. And so all the error process we know or work with for this kind of harmonic oscillators are local in phase space. So A, maybe A diag, maybe dephasing, all of this acts locally in phase space. So the idea of bosonic codes is to encode the information non-locally, to delocalize this information in this larger Hilbert space. And then, because you're correcting directly at the qubit level, you can use simpler codes after. All right, so let's start with the first example, transmon qubits embedded in the surface code. So thankfully, David Divicenzo explained everything about the transmon qubits, so I don't have to tell much. The qubit is encoded in the 0-1 energy subspace of a superconducting circuit. Then you embed it in this large surface code to correct for both the bit flips and the phase flip errors. And it's estimated that today you need around 1,000 physical qubits to make one logical qubit. So logical qubit is, say, 1 to the minus 6 logical error rate. And then in practice, how does this look like? You have some circuit, and you can like write the energy of the circuit, the classical Lagrangian, and then quantize it, as David Divicenzo showed. And then you do a lot of approximation, and you end up with a Hamiltonian that describes your qubit, in this case coupled to a resonator to read it. So you don't really need to look at the details of the equation. It's like just an example to see that For a given superconducting circuit, you have a big model, a Hamiltonian and some loss operators, parameterized by some parameters that describe your circuit. So this approach is sponsored by mostly Google and IBM, like a lot of other groups, but the bigger player here are Google and IBM. And it's been demonstrated experimentally at the qubit level, full control of the qubit, with some lifetime. And very recently, last year, the error correction was demonstrated experimentally with a logical lifetime of 300 microseconds. All right, on to the second approach. So this is the approach the startup I work with is following, and also Amazon was a quantum section. And so the idea here is based on bosonic codes. So I told you need to choose an encoding, and depending on the encoding, you will do a different bosonic code. So JKP is one encoding. Here the encoding is cat qubits. And so the idea is that your logical states are going to be coherent states of this oscillator. So you're going to say, this is my 0 state, and this is my 1 state. And as I told you, because you have local errors in phase space, there's very little chance that you actually jump to the other side of the plane, which in this case would be a bit flip error. So the qubit natively protects for bit flip. Okay, the further the states are apart, the better you protect for bit flips. And so you can use a simple code on top, a repetition code. It's estimated that you need like roughly 15 of these qubits to make one logical qubit. But of course, they're a little harder to make because you work in this larger Hilbert space and you need to implement this encoding. And in practice, how does this look like? Well, you also have a circuit. It's a different circuit, but the same kind of circuit we saw in David's lecture. You also can write the Lagrangian, do a bunch of approximation, and you end up with a very reduced model. And so just to give you a gist of the idea, so the model here is like you have no intrinsic dynamics, and you have some dissipator in A2 minus alpha square. And you can see that here the kernel, the steady state of this, is a two-level, like a two-dimensional system defined by the minus alpha and plus alpha coherent state. So this is going to be your qubit subspace in which you work. And this whole electrical circuit is engineering some mechanism that will stabilize this qubit within the large Hilbert space. The picture you can have in mind is that if I plot, say, the flow of the trajectories in phase space, what this circuit is doing is that it's making these states attracting states, okay? So anytime you have some perturbation, it will converge back to the pointer state, your logical state. And this is implemented in a way that you can also stabilize superpositions of these two states, which will be your plus state of your code. Anyway, the goal of the talk is not to speak about quantum error correction. I think what I just want to show is that superconducting circuits are very versatile. You can make very complex systems to embed like very advanced ideas. And now we'll discuss the challenge, one of the challenges we have when working with these models. All right, so just on some results, qubit part have been demonstrated experimentally with so this bit flip suppression up to 10 seconds. And the repetition code is a work in progress. So this is, if you want, slightly less advanced, less mature than the transmon qubit. All right, so I give you the secret recipe now to build a quantum computer. You choose some target dynamics to stabilize your qubit. You find a circuit that implements this dynamic. You build the circuit. You measure all the parameters, implement physical gates, logical gates, and quantum error correction, and you become rich and famous. So today we will focus on this step, the fourth step, which is to characterize the system you're working with. So the system is modeled by a Liouvillean, a parameterized Liouvillean. So the parameters that are entering in the Hamiltonian or jump operators are the one you want to measure. And this is really the goal of the characterization step, to estimate with a high precision all of these parameters. So an example is you might, for the transmon case, you might want to fit the simplified qubit resonator model, or you might want to fit the full circuit model with a Josephson junctions energy and the oscillator frequency. Okay, but now you may ask, why do we need to characterize anything if we design the circuit in the first place, right? So David explained to us, given a certain circuit, you can find the Liouvillean associated to it, and the parameters just depend on the geometrical configuration of the circuit. So supposedly, if you decide the circuit, you know exactly what are the parameters. Well, what happens is that this chip, so this is an example with 4 CAD qubits, they are fabricated in some like clean room environment. So this is a zoom of some section of the circuit. And what happens during this fabrication process is that you have a lot of impurities, and also the geometry you choose is not always like exactly the one that is actually made. So the circuit that is built is not exactly the one you asked for. And then this chip is about like a centimeter long. You put it in a sample holder here in the middle, and then in a can in the bottom of a dilution fridge, okay? So the only way you can interact with this system that you built is through like a classical drive, through this transmission lines. And so these 2 steps of fabrication and cool down are going to change the chip, the geometrical parameters, and make imperfections, which will result in this 4th step being necessary. You need to recharacterize your system, estimate all the parameters. All right, so what is the challenge in characterizing this system? Well, superconducting circuits are a bit of a double-edged sword. So on one side, you can choose the exact dynamics you want. You can engineer whatever you favor. But there are many parameters to estimate. You usually work in large Hilbert spaces. Every time you fabricate a new chip, the parameters change, and they also drift over time. And the physics is not super well described in some regimes, okay? As I showed you, we do a lot of approximations to find in the end the qubit space we encode. I think it's also important to point that the community is moving towards larger and more complex systems. So the first interesting applications, they start at 100 logical qubits. And so that's roughly 10,000 transmons and 1,500 CAD qubits. So these are absolutely huge circuits with a huge number of parameters. And you have new challenge when these circuits are built, new modeling issues and some unexpected effects. Yes?
So just to issue, the parameters could be like the capacitance and inductance.
Yeah, exactly.
And you want to optimize
you want to find, like, to estimate them experimentally.
Just estimate.
Yes. So the question was, where are the parameters, like, for example, the capacitance or frequencies? So the answer is yes. And you have the chip in the fridge. You can send pulses and measure pulses, like measure light coming out, and you want to find these values. All right. So this is the challenge we have, and I'll show you today's solution and why I think it's a little unsatisfactory. And then we can move on to, like, maybe new methods to characterize these systems. So how do we do today? This is a measurement graph by Google to characterize 2 qubits. So here, each little dot is a single experiment that was, like, handcrafted to estimate the value of one specific parameter, okay? So these experiments are built on physical intuition. You look at your system's dynamics, you do a lot of approximation, and you think, how can I estimate this specific parameter? And then you find the drive that will allow you to extract the value of the parameter. The data we are looking at is typically observable expectation values of your qubit, like sigma z. And this has a bunch of drawbacks. First, it's very data intensive. Second, the automation is very hard because you have all these measurements depending on one another. And all of the experiment has a specific fit, which works in some regime of the dynamics, etc. And yeah, lastly, you typically restrict your understanding of the system to regions where you understand very well what's happening. Otherwise, you wouldn't be able to make an experiment to fit a parameter in the first place. And so, okay, this is a claim. Not everyone agrees, but I think we need more automated methods to scale to larger devices, okay? And I think for this, we might need more expressive data than this expectation value we're working with today. So that's nice to say, but what data could we use? Well, if there's one thing you should remember from this talk, and that's why it's written in big, is that what we consider as projective measurements in superconducting circuits are always time-averaged continuous measurement. So we can only do like continuous measurements that we average for, say, 200 nanoseconds. And so typically what we do is heterodyne detection of a field. These readout devices that are connected to our system are actually amazing probes. They are connected to the system and they spit out a huge amount of data, but they're mostly used to measure sigma z of your qubit projectivity. So this is a bit of a gross picture, like a big picture. It's not always true, but it's just to give you the idea. And then because these circuits have very fast dynamics on the order of a few hundred nanoseconds, you can typically sample a huge amount of trajectories. So for a 1 microsecond measurement, which is already a pretty long measurement, you have a million of trajectories in 1 second. Now it turns out we have a very good formalism to describe this continuous measurement, the stochastic master for equation formalism, which describes how the state depends on the continuous time signal. So the mathematician in the room may frown a little bit at seeing this dyt over dt. I'll come back to it later. So as you know, the stochastic master equation mixes the average Lindblad evolution and the measurement back action, which I've not written precisely here. The expression depends on whether it's a jump measurement or diffusive measurement. And the stochastic process driving the equation can be either Poisson or Wiener, as you know from Pierre's lecture. So now the data is, okay, so, and you can also repeat the experiment. So you can always start from the same initial state and repeat the experiment. So the data looks like a collection of continuous time trajectories for your measurement. Well, actually, that's not true. So there is something that looks specific to superconducting circuits, but we don't really have access to this data. And the reason is that this chip that I showed you, this chip here, is at the bottom of a dilution fridge, and it's read out through an amplification chain, which is made of a lot of components, and ended by an analog to digital converter. So let's talk again about this quantity, I of t. Maybe I'll go to the other side. It's not a really well-defined quantity. It's used in a lot of textbooks and paper, but it's, if you want, it's defined in the sense of distribution, like Dirac delta functions. So it's only defined once integrated against some function. This value is defined, and you can consider it a notation for this, where this is an Ito process, and this is well defined as an Ito integral. Okay, so we can consider I of t as a notation. It's just used a lot. And so in practice, what is this f here that appears that makes your measured signal physical? It will be the impulse response of the acquisition chain. And as I told you, this chain is ended by an analog to digital converter. And this is going to convert your time continuous signal in a discrete time signal. Okay. So the actual data you have is this discrete time record for each measurement you run. So this is a little scheme. You have some sketch of the continuous time diffusive signal here. In this case, it's filtered by like a rectangular function on small windows delta t. So these delta t are typically on the order of 4 nanoseconds for superconducting circuits. And then so you average over each little window and you get a 1 value for the signal. Okay. And then of course you can, the filtering function can be made more complex. This is an example. And so in the jump case, you can think of the signal as a sequence of zeros, and sometimes you have a 1. And the filtering takes into account the fact that you don't know exactly when the detector clicked. You just know it clicked in some time interval. And in the diffusive case, you have a sequence of real valued data. All right. So the new question is, how do we estimate the system parameters from this data, this discrete time record? And actually, there are 2 existing methods. And the goal of this slide is to briefly show the method and maybe to explain why they are not used in practice. The first method is Bayesian inference. You can find the parameters as the one that maximize the likelihood of the data. This uses the information in an optimal way, like from a Bayesian perspective. But the issue is that it's exponentially costly in the number of parameters. So you will need to sample this likelihood in a huge parameter space. And it also doesn't take this important filtering into account. So if you remember Pierre's lecture, typically you write the probability of the data given the parameter. So this is like a discrete record, R1 to Rn, as a trace of the succession of some cross map, depending on this result. So here, this is a composition symbol applied on the initial state. And then the parameters are paraphrasing maybe the initial state and the cross map. And so typically all these schemes rely on a discretization of the stochastic master equation. Now, another approach which emerged recently with machine learning. So one way, for example, is to train a supervised neural network, where you feed to the network all the trajectories and you ask him to give you the corresponding parameters. And you train this for a lot of parameters and a lot of trajectories. This is quite general, but it requires a very large training set. And you also need to adapt and test the architecture every time you add a parameter or change your modeling. So it's not very handy. Yes?
You inverse problem, why give parameter?
So the inverse problem is I'm going to give to my network trajectories that I measured, discrete time trajectories, and I want the output of my network to be the parameters. And when I say learning, how you're going to do this is you're going to start with a network that is uninitialized you want, which is going to give like random garbage noise at the end. But little by little, you're going to put in a new trajectory and give the corresponding parameters and tune the knobs of the network. So it learns what are the parameters corresponding to some trajectories. If you want, it's exactly the same way we learn, like we teach neural network what is a cat and what is a dog, but you can do this for like any problem. Okay, and I think the shared drawback of these two approaches is that it's very hard to understand how the parameters are fitted from the data, okay? So in practice, you arrive in the lab, you're very happy with either method, you try it experimentally, and it doesn't work. And then you always question whether your method is not well implemented or whether your modeling of the system is incorrect. And you never know which one to trust, and it's difficult to debug this method. All right, so the proposition of this talk is to do something simpler, okay? Maybe something in between using the full trajectory data, but a little bit more involved than just using projective measurements. So that's part 3, sorry. It's the simple method we propose. Okay, so what is difficult in this problem is that there is a gap, a practical gap between what the theory predicts. The theory tells you how the state depends on the continuous time signal and what you actually measure, this discrete time record, okay? And so what we propose is to fit the correlation functions, and I will explain next slide what are these objects, but you can think in your head the mean or the autocorrelation of the signal. So we propose to fit these correlation functions with an exact formula that I will show you in a few slides. So basically you have some parameters, you generate some continuous time trajectories that are digitized by your amplification chain, you compute experimentally some correlation functions, and then you fit them with the formula you have, for example, with the least square fit. Okay, so what is a correlation function first? As you know, a random variable, x, is fully characterized by its moment. And for a stochastic process, like IPhT, it's the same. It's fully characterized by its correlation functions. And here, the little e is the big E actually, is the average of our all measurement records. And so what you're going to do is take your data and reduce them by computing some correlation functions of the discrete time record. So this is an example of what you would do experimentally. Say you have this trajectory, your data points are here. The 3-point correlation functions between bin K1, K2, K3 is like you multiply these 3 data points, you multiply these 3 data points, you multiply these 3, and you take the average, okay? And this is your experimental data, your estimate of the correlation functions. Yes?
Why it's more natural to look at the expectation of I than the expectation of Y?
It's the same. Yeah. So if you look at the expectation of Y, because you integrate with so the reason people use I is that if you look at the expectation of Y, it will grow with time, increase with time, because you integrate the dt in front of. So people like to think at I because you look at the slope, which is linked to the observable. But it's really the same. This is mostly to connect with notations used in the experimental community. Okay, and so this is a bit idealistic. In practice, you're going to look at maybe multiple correlation functions at different times. And also, you're not going to be able to compute them exactly. So, okay, sorry, this is supposed to be a straight E. You're going to compute estimates of these correlation functions because you don't have an infinite number of trajectories. All right, just to give a rough idea, I said the digitization time is 4 nanoseconds. So for 1 microsecond experiment, that's 250 points for your discrete time record. And if you do 1 second of experiments, that's 250 million data points. And that maybe explains why the Bayesian method and machine learning methods are very demanding numerically. So here is this reduced data set. If you look, for example, at the first point, like the 1-point correlation function and some of the 2-point correlation is just 500 data points. So it's much more usable. And I have an analogy for the method. I thought I would show it to you. A classical analogy. So if you take a pendulum with 2 parameters, its length and its mass, and you set yourself the goal to find the length of the pendulum, okay? And maybe you want to impress your friends, so you don't want to use a ruler, but do something a bit more fancy. Well, you can write the equation of the dynamic for the angle of the pendulum. And then you're going to say I'm going to stay in for smaller angles and approximate the sinus by just theta. And then you recognize here the equation of a harmonic oscillator with a period 2 pi square root of the length over g. But the way you're actually going to measure this is by looking at your pendulum. This is an eye. And you're going to continuously measure the position of your pendulum. And from this continuous position measurement, you're going to perform compute statistics. So for example, the period that you will link back to the system parameters. And so what we propose is to do exactly the same. We're going to continuously monitor a quantum system, compute some statistics of the signal, and then we have a formula linking the statistics to the system parameters. What's a little different is that in quantum mechanics, we need to take into account the back action of the measurement, but fundamentally, it's really the same idea. All right, so what are these formula? I have 3 slides on the theory. The first one is about the history. So first, maybe, okay, a naive way to compute these correlation functions would be to simulate the stochastic master equation for like a lot of time and average, but this is both expensive and imprecise. You will convert to the result in square root of the number of trajectory. And it turns out it's a bit of a miracle, but there is an exact formula to compute this quantity here. And this formula doesn't, you don't need to simulate trajectories. It only depends on the stochastic master equation and the initial state. So it's very, very efficient to compute. Historically, this has been proposed by Antoine Sillois in 2018 for the diffusive case. Then we had a paper at the beginning of my PhD with Pierre and Antoine Sillois with a simpler proof and some efficient numerics to compute these formulas. And then last year, we published a paper with an even shorter proof. It's just 1 column and a demonstration on numerical examples of whether this works, whether you can actually fit parameters using these formulas. All right, so what are the formulas? First, I'm introducing some what we call correlation superoperator. So it's just operators that depend on the jump operator that is measured, and the detection efficiency, and then the Dhar rate. And they have different expressions for the jump and for the diffusive SME. And now we're going to look at the formula for the sharp signal. So I told you, okay, what I call the sharp signal is IPhT. And I told you this is not really a physical quantity, but it's very interesting from the theory point of view still to look at this object. And so as you'll see, the formula is very simple. So to compute the expectation value of I at time t1, I at time t2, etc., up to I at time tn, you start from the initial state, you apply the average Lindblad evolution up to time t1, and at this time you insert the correlation superoperator depending on the detector you're using. Then you evolve with the Lindblad evolution up to time t2, you insert the correlation superoperator, etc., up to the final time. And this gives you some weird operator. And the trace of this guy is exactly the quantity you're looking for. So this is very cheap to compute. Like if you can simulate Lindblad, you just need to simulate Lindblad and then apply this correlation superoperator. Now what we really care about is the correlation function for filtered signal. And in this case, it's slightly more involved. You need to solve a system of coupled linear ODEs with a state that is augmented, okay? So this is an example where we compute the expectation value for a signal filtered by F1, some function, and another signal filtered by F2. And it's going to be the trace of some state at a final time. And this state appears here. It evolves with some other state in this big, large linear ODE. So maybe to explain, this rho dot equals L rho is the regular Lindblad evolution. And then for rho dot 1, you also have the Lindblad evolution plus a source terms that depend on the filtering function and the correlation superoperator that will be applied on rho. And so you're just going to evolve this large system of ODE, okay? And at up to a big time, a time that is larger than any time in the support of F1 and F2, you track the trace of this guy, and it's going to give you this quantity. What's important here is that the numerical cost of solving this is the same as solving Lindblad. So the generator has a block structure, so you can vectorize the computation. And it's also very cheap to compute the gradient of this numerically. So computing the gradient doesn't depend on the number of parameters. So you can estimate 100 parameters with this kind of method. All right, and I think importantly, this bridges the gap I told you about. I told you there is a gap between what the theory predicts, how the state depends on the continuous time signal, and what we actually measure. So this gives all the statistics of the signal you actually measure experimentally. All right, the third part of the theory is some bits of the proof. I'm not going to show everything, but just give you the general idea of how we find these formulas. So for a random variable x, characterized by its moments, you can find them by looking at the derivative, the straight derivative of the moment generating function, which is the expectation value of exponential tx. For a stochastic process, we're going to use the exact same object, except that we're going to look at the stochastic process at different time. So instead of a function depending on a real valued parameters, we're going to have a functional that depends on a function to be able to touch different times. So this functional is here. It's the same formula than this one, except we, instead of having t times the random variable, we have j, some function, times the signal. And then you can link both the sharp signal correlation functions and the filter signal correlation functions to this formula. So the sharp signal is going to be functional derivatives of this one instead of straight derivatives. And for the filter signal, it's going to be partial derivatives for this function that you put inside. And so, okay, the idea here, if this is a bit obscure, is that if you can compute this object, then you have the correlation functions you're looking for. Another question is, why is this easier to compute than this? Well, it turns out that you can write this object as a trace of a peculiar state. It's not a density matrix. And this state is the expectation value of, so this term here, times the state at t. And here, it's a bit magical. If you apply Ito's lemma here to this state, you will find that it obeys a very simple linear differential equation. And this differential equation is like a Lindblad master equation, except it's not Lindblad, it's Lindblad plus additional terms that depends on the correlation superoperator and on the function j that you're using. And then, so if you want the formal solution to zj is a trace of this guy. So it's going to be the time-ordered exponential of the generator, which is written here for the jump SME and for the diffusive SME. Okay. And then if you apply this formula or this formula to this equation, you find back the formula I showed in the previous slide. So this is the kind of techniques we use to derive these equations. All right, and so I'll conclude with 3 numerical examples. I'm going to be a bit brief. I'm going to skim through the examples. It's just to give you an idea of the kind of system we're looking at. The overarching goal is to calibrate to characterize the systems I showed at the beginning. So full-fledged huge superconducting circuits. So the question here is, does it really work? Like, given a system, can I actually estimate the parameters from the correlation function? All right. For this example, we generate fake experimental data. So we simulate numerically the stochastic master equation for a lot of trajectories. And we simulate for a very refined time step. And then we integrate to actually have this discrete time signal similar to what we'd have experimentally. Then we compute the correlation functions, an estimate, and we do this least square fit. So at the top right, you see 3 trajectories for the diffusive stochastic master equation. The very refined one, the one digitized with a small time step, and the actual one digitized with a realistic time step. And this is the same for the jump equation. So the first example is a driven anharmonic oscillator. And I told you I'm not going to show everything on this slide. The question is, can you estimate all the parameters entering here? So the self-care, the real and imaginary part of the drive, and the measurement efficiency, where here your signal are heterodyne measurement of this system that are digitized, as I told you. And so I like to ask when I have an experimental audience, well, which experiment would you actually do? What would you design to estimate each of these parameters? And so what we propose here, so we are in the system steady state. So the 1-point correlation function is going to reduce to a single value, which is not going to let us fit these 4 parameters. So we're going to look at the 2-point correlation functions. And so the 2-point function, so we don't see it very well, but it's this blue dots here, where the error bars are because we use a finite number of trajectories. And then we feed them with the theory in red, and we're able to recover all the parameters here with some error that depends on the number of trajectories you use. So if you use more trajectories, you will reduce the error bar here, and you will find the parameters with a smaller error. All right, second example is a driven 2-level system, so just a qubit with some detuning, a drive, and a decay rate. In this case, it's an example for a jump detector. You start from the excited states, and the question is, what experiment would you do to estimate the detuning, the drive strength, the decay rate, the Dhar rate, and the efficiency. And in this case, you can just look at the one-point function, the blue curve here. You fit it, and you find all these parameters with good precision. And the error bars here are estimated by some sampling, which means, right, that's perfect, which means you're going to take chunks of all your trajectories and run the fit independently for each chunk, and then you compute the variance of the estimated parameters among other chunks. And this gives you like the kind of bootstrapping method to get the error bars. The last example, same, I won't detail it too much, but it's an example we had from our group paper from 2023, where we had this weird dynamic I showed you on the board to stabilize this bosonic codes. And in this case, we were measuring with homodyne detection the signal leaking from the system. Three of the parameters were very hard to estimate using regular classical method. So they ended up being estimated with more than 10% uncertainty. And to gain confidence in the result, we fabricated, cooled down, and measured another superconducting chip. So one question when I arrived was, is there a better way to estimate these three parameters? So it's actually a difficult case because the system has some symmetry. The UV line I showed you, it commutes with a parity superoperator. And as a consequence, all the odd order correlation functions are null. This is a general result, but I will not detail it too much. And it also turns out that the two-point function is degenerate. So if you look at different combination of parameters, the two-point function, the curves are superimposed, okay? So you need to go up to, so there's two solutions. Either you go up to the 4-point function, and this will actually lift the degeneracy. Or another solution is to use the controls available and to measure the two-point function in different combination of controls. So in this case, we could vary alpha 2, measure the two-point functions in a different configuration. Okay, so this is again numerical data, and fit the two-point function to recover the parameters with good precision. All right, I'll finish quickly. What are the limitations and advantages? So limitation is that you need a parameterized model of your system. I think it's okay because if you're missing an important term, you will actually see an unexpected bump in the correlation functions you're trying to fit. It will rather result in an incorrect fit than a bad fit. Then it's not an optimal method, the data is averaged. If your efficiency is low, that's fine, because the higher order correlation functions, the information there will be washed away, and there is no theoretical guarantees. It's a bit of an empirical demonstration that it works. And then the advantages is that it's fairly general. It works for any stochastic master equation. So I've showed these examples and discussed about superconducting circuits, but it basically works for any continuously measured quantum system. It's quite simple, so the theory directly models the available experimental data. Experimentally and numerically, it's very easy to experimentally to compute these functions. Numerically, it's just solving an ODE and doing a least square fit. And as I told you, it's efficient numerically. It doesn't depend on the number of parameters. And finally, and I think importantly, you can build intuition about how each parameter is fitted from the correlation function. And this is very important to build confidence in the result and to test candidate models and to validate your model, maybe in some weird regime of the dynamics. This is a jump example where we keeping all the parameters fixed, we're varying the detuning, and you see that it changes the period, the drive strength changes the oscillation amplitude, and the detuning the original point. And so you can really develop intuition for your system about what the correlation function look like. And when you measure them, if there is like an unexpected bump, it's not even necessary to run your fit. You know that your model is incorrect. All right, I will conclude with some teasers and then a proper conclusion. So what are the teasers? The first teaser is that I have a poster on a library called Dynamics. It's open source. For this project, we had to simulate like millions of trajectories for very large systems, bosonic modes. And so we use a combination of software and hardware tricks to make this efficient. So if you want to discuss, you can catch me outside or come to my poster. The second teaser is about Howard Wiseman lecture next week. So the fact that we see the same structure for the jump and diffusive stochastic master equation for the correlation functions was a hint that led to a new way to formulate a stochastic master equation, a way to rewrite them. And so you will see this next week. And the last teaser is about Antoine Tillois's talk. So Antoine Tillois is my second supervisor, because I lied to you a little bit. I said we bridged the gap between what's measured and what's and the theory, but we just partially bridged it. We gave the statistics of the signal, but we didn't say how the state of the system is conditioned on this digitized signal. And so I like to think of this result as a middle way between having complete time information, the complete trajectory, as described by the SME, or absolutely no information, as described by Lindblad. In practice, you have small time averaged information, and the question is, what is the state in this case? And so Antoine will talk about the results we have in this regard. All right, this concludes my talk. Everything is detailed in this paper if you're curious. So thank you for your attention.
Thank you, Pierre, for a very nice talk.
I have basically two questions. First one was pretty early in your talk about this delta T.
Yes.
So I wanted to ask about a few considerations there. One is that, I mean, I was following, I think, the argument of what determines that. Part of it is the bandwidth of the measurement chain.
Yes.
Now, sometimes that means you have actually a much longer time, like if you use a narrowband JPA.
Yes.
And so then it would be 100 nanoseconds or something like that. But if you use more modern chain, like with a broadband amplifier tuba or something, then it could be smaller than that.
Yes.
You know, you have multi-gigahertz bandwidth, so you could go down to half a nanosecond. But is part of the argument that you don't want it to be smaller, at least in the sort of old-fashioned method, because you just have too much data, so you should boxcar it anyway?
So I think ideally, if you can have a smaller delta T, indeed you will resolve better the trajectory and the dynamic of your system. So
you would surely want to use that if you're doing correlation functions. You'd want to use the full bandwidth to acquire the correlation function, no?
So what's important is how delta T compares to the time scale of your system. Typically, if it's very, very small compared to the time scale of your system, you can use the SME, like the continuous time trajectory, and discretize delta T. The reason we developed this theory is that because in superconducting circuits, the time scales of the dynamics are getting shorter and shorter as we move towards systems with like better engineering. So you can think of transmon readout, which is getting shorter and shorter. And so we think we might challenge the acquisition time and have a delta T which is comparable to the system. But then indeed, as you say, it's also nice to compress a little bit the data to not have a very, very short delta T. Yeah.
One other very small question. I noticed that even in the simple examples, I think in example 1, there was a parameter kappa you just didn't estimate.
Yes.
Was there some reason why that would just get skipped?
Thank you for the question. So the reason I didn't estimate it is that in this typical example, it's super easy to estimate with a spectroscopy experiment. And so not saying we should replace all the experiments that exist. If we have very good experiments to estimate some parameters, you can use them. So it turns out that you can also include it in the fit. It's in the appendix. And you can also estimate it from these correlation functions. And then you will get a slighter, higher error because you give it a bit more liberty to fit the parameters. But you can also estimate the kappa to a good precision with this measurement. And if it were not the case, so
you could formalize that by introducing priors for the variances or something like that.
Exactly, you could build like a Bayesian model, yeah. So this is rather crude. It's just a square, like a least square fit with any unbounded parameters, but indeed, you can do more sophisticated fits.
Okay, thank you.
Thank you for the question.
Thanks for the very nice talk. Just a detail. At some point you said that the maximum likelihood is exponentially extensive in the number of parameters.
Yes.
Doesn't it depend on how the parameters relate to each other? Like if I have a set of orthogonal parameters, that shouldn't be the case. So how general is this?
That's a good question. I guess it also depends on the task you want to do. So whether you want the full posterior distribution of your parameters or not. What I'm saying is, generically, if you have 10 parameters to estimate, then this is not usable as it, except if you really have some very specific cases. And as I was showing, the systems we want to estimate have like 10s or 20s parameters. So it's very generic, I agree, but I think it's a good order of magnitude to have in mind. Thank you for the question. Yes.
Okay, well, can you hear me now?
Mm-hmm.
Yeah. So what I wanted to know is, could you just go back to that same slide that David was pointing at?
Yes.
Because you had, your errors were in kilohertz, right?
No, yeah. Sorry, this is, I'm estimating the value to be 100 kilohertz plus or 1.
Plus minus 1 kilohertz,
Yes.
yeah. So what I wanted to ask you is, if you take transmons, for instance,
Yes.
oftentimes you can have like, there's one frequency which is at 5 gigahertz, there's maybe like couplings which are at hundreds of megahertz, and isotropies which are a few megahertz.
Indeed.
And so parameters can run 3 orders of magnitude, 4 orders of magnitude
Yes.
different from each other. So what I wanted to know was, if you wanted to suppress errors by 3 orders of magnitude or 4 orders of magnitude in comparison to the largest number, how well does your scheme do?
If you want to suppress the, so why would you want to suppress the errors?
So I
compared
want
to the
to
large,
estimate something that's 5 gigahertz, 500 megahertz, and 5
Yes.
megahertz, and at a rate which is
Okay,
at
okay.
an error bar which is
Yeah.
lower than the 5, so that the 5.
That's a good question. So I think in this case, you wouldn't use the same data for the 3 fits because the timescales are so different. You would use an experiment which reveals the smaller timescales and also the longer timescales. So different experiments, indeed.
Okay, and that's the way that you would propose to actually handle that problem. Could I just ask one quick follow-up question?
Yeah.
How well does spectroscopy do in comparison to you right now? Because presumably Google and all these folks have like fairly good enough gates before they start doing error correction, right? I mean, just to ignore the very
Yes.
latest result. They've native gates they've gotten up to like 99%,
Yeah, yeah.
and so they seem to know their parameters really, really well. So
Indeed,
is it-
indeed.
can you compare these numbers to those numbers?
Yes. So indeed, I think if you design a specific experiment, for example, for the decay rate here, you might be able to estimate it with a much better fidelity than this one. I think these schemes are used to maybe automate the measurement process. So maybe you get a rough estimate for a lot of parameters at once. Maybe to estimate parameters that you're not sure how to fit, some parameters that are hard to estimate. But as I was saying, I don't think this should replace like all the existing experiments. And so I'm not exactly sure how precisely they fit the parameters of the system, probably a bit better than 1% error. But it's not like 10 to the minus 5 error either. We have some still some variance of the estimated parameters.
I mean, this looks amazing. And are you just being conservative about this in the sense that if you took more data in, would you be more trajectories in? Would you be able to estimate it much better than?
Yeah, so the error here will scale, the radius of the error will scale as square root of the number of trajectories.
Unbiased estimate, okay.
Yes. So if you want to divide the error by 3, you need that data types more trajectory. So it's the same as any usual estimation problem. So if you want to have a 10 to the minus 5 error here, well, this is not going to work. Like this is not sensitive enough to this parameter, or you need to average for quite a long time. I think given the timescales we have, as I told you, it's relatively easy to have like 1 million trajectories. I think this fit is for 100,000 trajectories. So, okay, maybe for some parameters, you want to monitor your system for like 30 seconds, and then you have a lot of data. Thank you. Yes.
Can I ask a follow-up question to this, actually? You mentioned at the end of your talk that you can use these estimation procedures to inform or to learn about how good your model selection is to start with, right? Any estimation procedure depends on actually having a model that is correct to start with. This is true of any of the examples that you've given. And Sai is mentioning that Google, etc., they're quite good by now in knowing their own parameters. I had understood that part of where the noise comes from that is left is that they're just misspecifying the physics a little bit, right? There's a larger Hilbert space or whatever.
Yes.
Could you comment on that?
Right. So it's also maybe one of the big claims of this talk is that because we want to do experiments in regions where we really understand exactly the physics, we confine ourselves maybe to the 0-1 level of the transmon, and we don't drive the readout resonator too strong. Otherwise, we just don't know what's happening. It's hard to describe. And so maybe a good example is this 5% correction to the Josephson junction Hamiltonian that David mentions with this cos to phi. I think it's both fascinating and a bit frightening that it's been like maybe 50 years we have a Josephson junction and we never identify this term. And the reason is that if you remain in some corner of your parameter space, you will never see the full dynamics. And so, yeah, I think one idea maybe is to be a little bold and drive your system more strongly than you would and actually check whether your modeling is correct or not and what do you need to add to your model to cover more of the parameter space. Yes.
Okay. I may have a very naive question, but why do you have to work in continuous time, assuming that you have a continuous time measurement? Because in practice, you have a discrete time measurement. So
the question is, what is, you could say, okay, this is all POVMs where you apply the POVM and small. The question is, what is the exact POVM you apply on some small delta t when your measurement is average heterodyne or homodyne measurement? And it's not easy to derive the POVM you have on like corresponding to this measurement procedure, which is continuous measurement and then you average. It turns out that you will have the answer in, disappeared. You will have the answer to this, how you write this exact POVM in Antoine's talk next week. But indeed, it's another way to see this as a discrete time measurement where you have a specific POVM at each time. I think the reason this talk exists is that because we didn't know how to write this POVM before. Thank you for the question.
Could you use this approach also for any stochastic process? Like I could, for example, the pendulum with noise, just a classical layer. If I wanted to estimate parameters using correlation functions in this, would that also, it's the same thing or?
I'm guessing yes. Funny, I've never thought about it. I'm guessing they already do this probably. But yeah. So the question is, can you derive an efficient formula to compute the correlation functions depending on the system parameters? Maybe the structure of our SMEs are simple enough to do this. Maybe it's not possible, for other systems. Yeah, I don't know, but supposedly yes, like the approach works.
Okay, so if there are no further questions, you have? Okay, then let's thank Pierre again, and we'll meet tomorrow at 9:30 morning.
Thank you.